Alright, let's talk about test 3 and its solution. Again, I'll let you look at the blank test and try it for yourself. I'm just going to talk to you a little bit about how this test went and what's the intention of it. State the following theorems. Make sure to include preconditions which are necessary for the theorem to hold true. So yeah, these are the three big theorems of differential calculus. There's also this extreme, there it is, the extreme value theorem, but there's also the intermediate value theorem. In some sense, the intermediate value theorem and the extreme value theorem, those aren't really theorems of calculus. They're really more theorems of topology because they're based on compactness or connectedness, and those are topological ideas. And so, but Rolle's theorem and the mean value theorem, of course, are very much theorems of differential calculus, of course. And there they are. We talked about those a little bit in previous videos, so I'll leave it at that. And so, you gotta, how do you memorize a theorem? I don't encourage you really to memorize it as it's stated in the book or something necessarily. You can do that. That's one way, but I'd much rather that you really understood it so you can say it something like I have stated here. Show that 2x minus 1 minus sine x equal to 0 has exactly one real root. So this is a kind of a different sort of problem. So let's look at the solution here. First of all, if I call this thing f of x, you notice that df dx is 2 minus cosine x, which is greater than or equal to 1, so it's clearly positive, which means that the function is increasing, strictly increasing in fact. And if you notice that f of 0 is minus 1, whereas f of pi is greater than 0, that means that there exists some c between 0 and pi such that f of c is equal to 0 by the intermediate value theorem, since f is clearly continuous, right? If there was a second 0, right, then you'd be able to apply Rolle's theorem and find some other place where the derivative was 0, right? If there was another place where the function had 0, then we'd have f of c equal to f of c2 equal to 0, and that would imply that f prime of some point was 0, but that's impossible because f prime is greater than 1 everywhere, so no second real 0 can exist. So this is a proof by contradiction using Rolle's theorem. So let's see here. That's kind of unlikely for the quiz. Let's see here. Problem 3. Let f of x be the natural log of x squared plus 4x plus 5. Locate all critical numbers and use a second derivative test to find local extrema for the function. So df dx is this by the chain rule and how logarithm differentiates. The denominator is an irreducible quadratic by completing the square, right? And so the numerator is the only thing we have to worry about for critical numbers. We don't have a division by 0 in this formula. And x equals minus 2 is the only critical number. And then I have to calculate the second derivative because I forced us to do it. And then let's see here. So you get that. When you plug in minus 2, you get 2, so it's a minimum. All right. Find the intervals of increase and decrease. By the way, that is a reasonable question for your quiz at the start of Calc 2. Problem 4. Find the intervals of increase and decrease for the function f of x equals to x plus 9 over x. Also classify any local extreme values of the first derivative test by the first derivative test. Again, this would be a reasonable question to have on the first quiz of Calculus 2. I do want you to know how to graph functions using first and second derivative tests and the relation between increasing and decreasing as it relates to the positivity or negativity of the derivative. These are important things to know about, and you should know them. Anyway, here are details. So differentiate, and then I make a common denominator. So basically x equal to 0 is a place where there's a 0 in the denominator. I think that's going to be like it's either a vertical tangent or it's a place where the function is not defined. Oh, look, it's a place where the function is not defined. So, okay, that's out. It's a critical point, but it's not a point in the domain of the function. So minus 3 and 3 are the other critical numbers. So these are the places where things can happen, minus 3, 0, and 3. And you make the sign chart plus, minus, minus, plus. the minus to minus is because it's squared there, so the sign of the derivative doesn't change. So you can read from that, it's increasing from minus infinity to minus 3, and also from 3 to infinity, and it's decreasing minus 3 to 0 and 0 to 3. But I need to break it up because 0 is not in the domain. That shows you that f of minus 3 is local max, f of 3 is local min. Great. Problem 5. Determine where this quartic is concave up or concave down. So I differentiate twice, find the second derivative, and then look for where are possible points of inflection. Those are places where this is 0, apparently at minus 2 and 3. Make my sign chart, concave up, concave down, concave up. Both of these places are points of inflection. Use calculus to find the point on the line y equals 3x minus 7, which is closest to 120. Your answer should include some indication of how calculus. Now, the reason I do that is because, of course, anybody who's a little bit with it would just draw a perpendicular line and go, oh, I'm done. But I really wanted people to use maximization of calculus to try to find this answer, so I forced it upon them, being the draconian monster that I am. But no, I mean, anyway, it's kind of an ugly problem. But the methodology is clear enough. You write the distance function from a point on the line, which is x minus 100 plus 3x minus 27 quantity squared, and then you try to maximize this. You look for the critical number, and then you can either use a second derivative test or check the first derivative test, or geometric intuition makes it clear that that has to be a minimum. So that's the closest point. It's kind of ugly. Here's a standard problem. You might have seen this in your college algebra class even, right? Because it's really just, it ends up being, you're maximizing or minimizing, I should say, a quadratic. So you just look for the vertex, basically, which is where dA dx is equal to 0. And there you go, anyway. Yay. Calculate the following limits using algebra or intuition. Again, limits at infinity, I don't think I'm going to, I'll just say it, I'm not going to put limits at infinity on the quiz, the first quiz in Calc 2. We will get back to limits at infinity before you know it. It would be good if you already knew these things, but again, I'm going to focus on the derivatives and the integrals to start with at least. Let's see here. L'Hopital's rule we will learn soon enough. Here's another. Find local extrema for 1 over x minus 1 minus 1 over x minus 3 plus 1. Find horizontal asymptotes. Horizontal asymptotes I won't ask you about just yet because that's limits at infinity, which we'll get back to eventually. I don't know. Okay, so there's that, and let's see here. F of x equals sinh x. Find the intervals of increase or decrease. Intervals concave up, concave down. So the f dx is cosh is positive, so the sinh is always increasing. Second derivative is sinh again, so it's negative below 0, it's positive above 0, so that's where it's concave down, that's where it's concave up. And of course you can kind of see that, right? Like so. And you can use Rolle's theorem to show that since sinh of 0 is 0, you can't have anywhere else where there's 0. Otherwise, it would contradict the fact that the derivative is positive everywhere, right? If there was another 0 of sinh, that would, by Rolle's theorem, say that there's some other point in between that second 0 and 0 at which the derivative is 0. But the derivative of sinh is cosh, and that's impossible. So that's a nice little bit to know about. Just one real 0 of hyperbolic sine. This problem is kind of nice. You have a smooth function, critical points minus 1 and 2. You know that the second derivative is negative for x beyond 1, above 1 rather, and second derivative is positive for x less than 1. What is then the what is the second derivative at 1? And how do you know that to be true from the given information? Find the intervals of increase and decrease. Let's see here. I said I know f prime prime of 1 equal to 0 since f prime prime is continuous by the smoothness of f. Right. To say f is smooth, this to say it has arbitrarily many derivatives and they're all smooth. So continuity forces f prime prime to be 1. Continuity of the second derivative. if you like, you can apply the intermediate value theorem to a neighborhood of x equal to 1, and note that the second derivative changes signs in such a neighborhood. So if you look at that, then here's the sign chart for f prime prime, and here's the f prime. How did I figure this out from that? Oh, because I know that I've got, I know that -1, I'm given that -1 and 2 are critical points, right? And I know that the first derivative exists because f is smooth, and so that makes this a maximum and this a minimum. Then the first derivative test forces it go plus minus and then minus to plus. And so I can figure out that f is increasing minus infinity to -1 and 2 to infinity, and decreasing on -1 to 2. This is a problem I'm proud of. Problem 13. If I had made this a cube, it would have been better, because then it would actually be physically a little bit more physically, dimensionally correct. But anyway, I'll let you look at that. I think that's a reasonable question. Just it's an application calculus to a particular formula. Here I am. It looks like I've decided to revisit the f of x equals polynomial times e to the cx problem again. This time, last time I asked about how many horizontal tangents were possible in test 2. In test 3, you see I'm asking about how many inflection points are possible. And the answer is again n, because when you differentiate twice, you still end up with, after the dust settles, a nth order polynomial. Whenever that 0 is a possible point of inflection, so you could have at most n inflection points. This is something I like to do, especially if a class has a problem that a lot of them don't get. A lot of times in the next test I'll ask something related to see if they've taken the time to figure out what it is they got wrong on the last test. You see, tests aren't just for grades, they're for learning, and if you're not using the test to learn, then you're really not getting what you should out of my class. Anyway, so that's all I have to say about test 3 here. I'll move on to test 4 momentarily. Thanks, guys.